Dear students, today we'll discuss certain important aspects about convex sets and functions. But I'm sorry that I have to go back to the old style of lecturing with just the slides and my voice at the back, because what's I'm observing that I'm trying to give this lecture with both my video on and also this slides on, but the video seems to get stuck in the middle, and so I've been trying to re-record it for a couple of times and then I gave up. And at least for today, let me just record it in this traditional way which I was doing in the beginning. So we have just learned about convex hull, learned about Carathéodory's theorem, and now let us make up a very simple set. Let us make up a simple convex set by taking the convex hull of a finite number of points. So that is the most simplest thing. So such a set is called a polytope. That C is the convex hull of say k number of points in Rn. Now, because k is the maximum number of points it has, it's natural that we can always represent any point x in terms of this k elements. Of course, you can talk about Carathéodory theorem. If k is bigger than n plus 1, of course, you can do it with n plus 1 elements. But it doesn't matter because you cannot have any element more than k. So, if k is more than n plus 1, you can always have uh, lambda i's between n plus 1 to k to be 0, right? That is, you can have certain lambda is dropping down to 0. So because we are choosing lambda between 0 and 1, every x can be represented in terms of these k vectors, and these vectors are called vertices, and this is actually a bounded and closed set, a compact set actually. So let me just give you a glimpse of what is a polytope. So these are it looks like a pentagon. Actually, it's not a it's a pentagonal region. It's a kind of five vertices and everything inside, the boundary and everything inside. So it's a closed bounded set. It's a compact set. So these points v1, v2, vk are called vertices of the polygon. It's also a polyhedral set because you can look at them as kind intersection of half spaces also. It's a bounded polyhedral set. So these points have special name called vertex. So it's called a vertex because there is no two distinct points in set C can be which can be used, or on whose line segment the point v2 lies. That is, there is no distinct x1 and x2 in C such that say v2 or v3 or v4 whatever, any of these points can be expressed as a convex combination of those 2 points. So if you can express say v2 in terms of say half of x1 plus x2, then v2 equal to x1 equal to x2. So there is no two distinct points whose convex combinations are any of these vertices. You cannot find any two distinct points. You take any vertex, there will be no two distinct points whose convex combination would be this. This is very special points, and these edges that you see here, the sides, these are called faces, right? In a more deeper polyhedral theory, but we are not going to get into all this at this moment. Possibly we are not going to discuss this in this course because that would lead too much of mathematical understanding. So let's just look at what this idea of a polytope can give me in optimization. Can we tell me something interesting about optimization? Okay, you know that for a convex function, a local minimum is a global minimum, but a local maximum and a global maximum are not the same, right? But the interesting feature is that for a convex function, for example, a convex function may achieve a local minimum but never achieve a global minimum but never achieve a global maximum. For example, fx equal to x square, it on the whole of R it never achieves a global maximum because function value just goes towards infinity. But if you take a polytope, say, then on the polytope a convex function will always achieve a maximum value, and that maximum value is achieved at a vertex. That there will be a vertex whose functional value would be bigger than the functional value of the function f over the rest of the set C. So let us consider x to be any point of the polytope C which say has k vertices. So by definition of the polytope, we have x represented as a convex combination of v1, v2, vk. Now, interesting feature about convex functions is that we already know that if we take two convex combination of 2 points x1 and x2, so that is f of lambda 1 x1 plus lambda 2 x2, where lambda 1 plus lambda 2 is 1, then this is less than equal to lambda 1 fx1 plus lambda 2 fx2. But can we extend it to more than two elements? The answer is yes. So that is what was the initial convexity inequality given by Jensen in I think 1889 or something like that. I just don't remember the exact year. So WBV Jensen, a Dutch scientist, and he Dutch mathematician, and he gave the equation as that the value of a function f over its convex combination is less than the sum of is less than the convex combination of the function values. That is what he says. The functional value at a convex combination of points in, say, a set in Rn, for example, is less than equal to the convex combination of the function values at those points. So f of x is equal to f of lambda 1 v1 plus lambda 2 v2 plus lambda k vk is less than equal to lambda 1 v1 plus dot 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 lambda k vk. Now, if you line up these fv1, fv2, fvk, one of the values has a maximum value, the functional value. Say that be, say, fvr, where r is some index between 1 to k. Then what do we see from here? We see that fx is less than equal to fbr, and x has been chosen arbitrarily. So we have proved that fx is less than equal to fbr for x element of C, which means fbr is the upper bound or the maximum value of fx over C, and vr is the vertex point where this maximum value is achieved, and that proves that result. We have been talking about convex functions analytically. We have not even showed you pictures of convex functions or concave functions. So let me show you a picture of a convex function. If you take a convex function from R to R, say, a convex function roughly looks like this. You try to do with fx equal to x square, you will see a similar sort of curve. So this is the graph of the convex function, and let us see what that definition says, that f of lambda x1 plus 1 minus lambda x2 is less than equal to lambda fx1 plus 1 minus lambda fx2. What does it say? So let us take x1 and x2 be 2 points on R, and let us take a point which is a convex combination of these x1 and x2. So we choose a lambda, say, between 0 and 1, strictly between 0 and 1. So there is a point lambda x1 plus 1 minus lambda x2. Let this point be here where I am marking just putting the cursor. And then at this point, let me compute the function value. The function value, the f value is given by this length, f of lambda x1 plus 1 minus lambda x2. Now let us look at these 2 points on the graph. This point on the graph, which is in R2, is a point whose coordinates are x1 and fx1, and this point whose coordinates are x2 and fx2. So now in R2, if you take a convex combination, so it will be lambda x1 fx1 plus 1 minus lambda x2 fx2. So we'll have finally a convex combination of these 2 points with the same lambda that we have chosen earlier would be a point of the form lambda x1 plus 1 minus lambda x2 as its x coordinate, and lambda fx1 plus 1 minus lambda fx2 as its y coordinate. Suppose it is here, but the x coordinate is same. So the x coordinate is the same as the one which we had done earlier, chosen earlier. So this distance that we see is the length lambda fx1 plus 1 minus lambda fx2, which is obviously bigger than the length f of lambda x1 plus 1 minus lambda x2. That is exactly the convexity inequality. So what does it say? That choose any point x1 and x2 and take the corresponding points x1 and fx1 and x2 fx2 on the graph of the convex function, join them. then the portion of the graph for the points x that is lying between x1 and x2 here on the real line actually lies below the chord or the line segment joining x1 fx1 and x2 fx2. This is a profound insight because it tells you that you take a pencil and shade the upper part of the graph of this convex function, you actually get a convex set. So upper part of the graph of a convex function is called a epigraph of a convex function, and that is mathematically expressed in this fashion. For a concave function, a similar story occurs where for any 2 points x1 and x2, the line joining these 2 points on the graph x1 fx1 and x2 fx2 actually lies below the graph of the function. So if you shade the part of the region below the graph of the concave function, then that part becomes a concave, that part called hypograph becomes a convex set. So here we have this epigraph of a convex function in R2 and hypograph of a concave function actually. So anyway, for a general function, you can define an epigraph in this fashion and an hypograph in this fashion. That is, you take any point here. So just suppose this is x alpha. So you just drop the x. So this is your x. So this is the fx value. And alpha value is somewhere here. So fx is always less than alpha, which is of course the reverse in the case of the hypograph. So there's a beautiful relationship between epigraph of a convex function and the function itself, and hypograph of a concave function and the function itself. A function from a convex set C to R is convex if and only if the epigraph of f is a convex set in Rn cross R. And it is concave if and only if the hypograph is a convex set in Rn cross R. This is not a very difficult result to prove, so I just leave it to the reader to prove this fact. And then we will move to a very important idea of continuity of convex functions. So we will talk about it in the next lecture. I hope you have got some feel of how intricately convex functions and convex sets have an interplay, whether it's a convex function always achieving a global maximum over a polytope, or whether this link between convex sets and convex functions through the use of hypographs and epigraphs, through the use of epigraphs and hypographs. So you see, concavity and convexity of functions is deeply linked with convexity of sets. For example, if you had taken a polytope and you had spoken about the minimum of a concave function, which is a hard thing, but a minimum of concave function would be achieved on a polytope and on a vertex. Now, if the polytope has an interior, it will be never achieved on the interior because of that minimum or maximum principle that we had learned when we were learning that every local maxima of a concave function over a convex set is a global maxima. After that, we learned that if you take a concave function and you want to minimize it over open convex set, then there cannot be you take not open convex set, just a convex set, and you want to minimize a concave function over the convex or set. You basically want to find the global minimum of a concave function. Then you will never ever achieve the global minimum on the interior. It will be always on the boundary if the set is closed. Similarly, for a convex function, if you are taking a convex set and you want to find a global maximum of a convex function, if the global maximum is there, then it cannot be on the interior. So in the case of polytopes, we clearly show that it is on the vertex. And we know that from the previous result, the maximum principle or the minimum principle, whatever you want to call it, depending whether you choose convex or concave function, we cannot have the maximum value in the interior for a convex function, minimum value in the interior for a concave function. So with these basic ideas of this talk was essentially about the interplay between convex sets and convex functions, and now we'll go to a more analytic study of convex functions by talking about the continuity property of convex functions. So thank you very much. We will meet very soon.